Hello, peeps.
YouTube. Hello, greetings everyone.
Greetings. And here we go.
Greetings.
So, hey Twitch, hey YouTube, subscribe. C++ 101, fit as roto, and fit progs too, right?
Yeah. But you are the host today.
Yeah, right. So, what are we going to do actually? I actually had a few ideas. The music is a bit loud for me. But basically, let me just verify. Okay, it seems to be working, right? Oh, thanks for the sub. And let me just refresh. Yeah, okay. Unstable. What do you mean? I'm very stable.
You're unstable.
I'm very stable. Okay, it seems to be fine. So okay, do you want bottom to top approach or a top to bottom approach? Yeah, we're starting already. So no, not that way, Azrato. No, I'm not in. Okay, I'm talking about like the algorithm thing. Okay, not.
Hello, Solaris.
Hello, Solaris.
How are you?
No, okay, Azrato. Okay. So let me rephrase that. Do you want me to start from very low level concepts and go to higher levels after that? Or do you want me to take a high level approach and go to a low level approach then? Basically, do you want me to start with like memory and that kind of stuff? Or do you want me to start with like general algorithms?
I think we can start with basics, low level.
Yeah, I was hoping for that.
Yeah.
Okay, so are you on Whiteboard?
Yeah, I'm on the whiteboard.
Okay, so do you know how memory works?
It's 0 and 1
What
with
is it?
addresses.
So ugly. Why do you have the link? Do you want people to join? Are you French? Yeah,
No.
we are. We are French. Frenchies. Okay.
You are Japanese now.
Me too. Oh. Hey. Baguette friend. But
You're
yeah.
a little Japanese.
Okay, so I'm going to explain to you quickly. Basically, you have, you know, the disk, right?
Yeah, beautiful disk.
So the disk has like memory, but it's like really slow to process, right?
Yeah. Because it's a drive spinning.
Because it's what?
It's a drive with spinning.
Speak a bit higher, please.
Alright. It's a drive.
Oh, yeah.
Disk.
Yeah.
Uh,
But basically,
Can I
it's...
wrote something?
Hmm?
Okay, so it's a big drive. It's a Sonic, and it's spinning fast because it's Sonic.
I suppose.
But it's very slow because it's mechanical.
Are we going through the internal workings of memory, stack and heap, etc.? Yeah, right now that's why we are going to do basically. And hi, how are you doing, guys? Good, thanks. What about you? And yeah, basically, to give you the plan right now, we're just going through the stack, the heap, and basically the reasons why we have a disk. Basically, disk how is it called? What's the thing that's... I guess the RAM and like the cache, right? And then you have the processors. Yeah, you know that. Nice. And basically, after learning that, we're going to see, for example, why we have in C++ std vectors and std lists, and like the pros and the cons. And well, you have the equivalents in any language. So for example, C# you have ArrayList and just linked list, for example. In Java you also have something like that. Yeah, it's kind of
language.
Very similar. So yeah, anyways, so yeah, the implementation actually doesn't matter much. Basically, the goal of the disk is to optimize the quantity of data you can store in. And it's doing that, but it means that it's not optimizing the speed that you process on the disk, right? That's why if you load a file, for example, from the disk, it's always really slow. And that's why, for example, with video games, you have some... well, it's getting slower. Because basically, if your RAM is full, it's starting to use the disk for memory instead. And that's why it's becoming slower. But yeah, you have the disk, then I guess you have the RAM. The RAM, what is it trying to do? I guess it's like... What?
Store data, but when we shut down the computer, it's cleared.
Well, it does that, but it's not necessarily the goal.
It's to store data, but read and write fast.
Yeah, that's it. So, less data, but fast to process. And basically, well, then you have, you know, your CPU. I guess that's part of the CPU. Well, it depends, but, well, anyways. Then, when you want to use that RAM, the thing is, it's loading some parts of that RAM into cache, right? So for example, the L1 cache. Well, you have different registers. Basically, you have different caches. So for example, L1, L2, L3, L4. And so what's the goal of that cache?
It's faster than RAM.
So yeah, it's basically less data. It's just the same thing every time, right? But it's faster. And the reason is that because it's closer to the processors. Like physically too.
Can you show maybe a CPU map?
That could be nice. CPU. Like the whole thing, or like a scale. Wait. Schema cache. Okay, I found something really nice. Basically, you have that. I guess, wait. What about that?
Oh, it's right on.
Okay, here.
Oh, you're smarter than me.
Hey, screenshot. So yeah, you have the CPU. And wait, what? I don't really remember. I don't know if memory. I don't really know the specifics, but basically, I guess CPU is like the processing unit. So yeah, it's like the processor. Yeah, so it's there. So yeah, you have the memory. This is the RAM. Oh, it's white.
Right in red.
Hmm?
In red.
Oh, yeah, I'm going to be orange because Amogus, right? So the memory is the RAM because a random access memory, is that it?
Yeah.
And then you have basically a lot of things, and you have the cache, and then you have the processing unit. So the processing unit is what's running computations like additions, like subtractions, like, you know, the move operations, you know, running the
Like everything
assembly.
in assembly, you know.
Yeah, that's it. So yeah, that's it. And what? And yeah, that's it. And like basically you have, for the processor, you have some registers, I think, where basically that's maybe like 16, or I don't really remember the specifics, but it's like very little, and you know, it's like to run operations. So that's why you can also, for example, you have something called SIMD that can run computations on batches of data. Do you know about SIMD? Or not?
No.
No?
No.
Okay, it's like processor-specific commands, for example, like functions that you can actually call from C, for example. And for example, you can optimize matrix multiplications thanks to that, because you can, for example, multiply 16 floats at the same time with a single function, I guess, with a simple process. Well, command, I suppose. So you can optimize with SIMD, but like basically you don't really have to worry much about that because it's like micro optimizations, and at the same time compilers can like use SIMD. Yeah, basically, for example, if you have a loop, a for each loop, it can optimize your for each loop with SIMD automatically. Anyways, so yeah, you have all of that. Hey, so now the question. We got the Dequeue. The question is.
You really should add I speak Japanese 9.3 rows.
The thing is, you have two types of arrays, you can say. You have, if we talk in C++, you have std vector.
Yeah.
And you have, I'm going.
array.
No, no, that's. Well, I guess, I guess you could say. Well, I guess you have multiple things actually. You have array, indeed, and you have list, or like forward list, for example, because list is actually forward and backward. So yeah, you have that, okay?
Yeah.
So let's start with std array, okay?
Okay.
What is it?
It's
Okay,
a
just
fixed number. It's a
just
fixed number of
yeah.
elements.
Continue. Sorry, repeat.
So we have to declare the number of elements at start.
Speak louder.
Ah.
Yeah, you're right. Just
Yeah. We have only 3 elements and we can change the number of elements at one time.
Yeah, basically when you put that, you allocate memory on the stack like in an array, like multiple elements. Because okay, let's talk about the stack right now, okay? So the thing is, when you start your program, okay? Well, for example, your C++ program is going to allocate a bunch of memory on the RAM for your program. So you have the RAM and you have a bunch of memory that is allocated. And basically, let's say you do int I, and like you create some variables, right? Well, it's going to allocate on the stack. Yeah. And the thing is, do you know about the stack or not?
Not really.
So basically you can, well, okay, let's talk about some higher level concept, okay? Do you know what okay. Do you know what that is, FILO?
No.
So it basically means first in, last out. Okay. And basically what you do is, for example, you have these variables, okay? So you have I and you have C, okay? Now, let's say you have some brackets.
Yeah.
It's creating a scope, right?
Yeah.
So basically you can have that with if conditions, with while loops, with for loops. You can have that for functions. You can have that, basically you can have that for a bunch of things, right?
Yeah.
But you can also put them like without any loop or anything in C and C++. And inside you can put some variables. Oh, well, this one is J, I suppose. Okay. And the thing is, at the end of a scope, this variable is destroyed. Yeah.
Yeah, it clears worm.
And the thing is, okay, so let's start the program. We allocate I. We allocate C. Then we have J that we allocate, right?
Yeah.
But then the brackets are ending, right? So let's say we have like another, we have a float, F. Then we allocate F. But like at the end, there's a brackets. So it's deallocating that. So it's removing that. Like with the FILO concept, basically, first in, last out. Okay? Because I will be the last one removed. But it was the first in. So we remove F and then J because we are ending the brackets. And then we can, for example, create another variable that is going to be k, and k is going to be allocated there. And do you know why a stack is used, basically? Why it's working like that, memory-wise?
Because outside the brackets we don't need var anymore.
We don't need what, sorry?
Var anymore.
What anymore?
Var.
Yeah, variable. Yeah, but like the FILO concept, like this general concept, why is that? Well, basically, because it's simple. Like, basically, because when we want to create a new variable, we need memory to allocate it. And we know where the memory is because we have all of our variables and we can just add, use the memory at the end and then add an offset. And then, you know, the memory is like deleted very easily, right? Because we just remove the last element to remove a variable. Well, the last variable, because it's on the stack, because it's like a simple variable, right? Is that fine with you?
Yeah, it's fine with me.
Okay. But then you have dynamic memory. And it's called the heap. So basically this was the stack. And it's like how your program works originally. But then you have the heap. And the thing is, basically, let's say you want to create, let's say you have, create.
Oh my god, it's a pointer.
So yeah, it's a function, right? Let's say you have, I'm having a function there. I guess we could go in Visual Studio Code, but that's fine. Yeah, that's fine. Let's say I want to return a variable, like create an object in that function and return it to use it elsewhere. Okay?
Yeah.
Basically, it's not working with the stack. Because if I create like my variable here, right? And if I try to return like the address to have a pointer towards that, if I allocate the memory here like that, well, basically it's going to be destroyed at the end of the scope, right?
Yeah.
With the stack mechanism. So instead we are doing we are using something that is called a heap. That is, basically you have a bunch of memory. And what we are gonna do instead is search for memory that is free, that you can use, allocate that, and basically potentially allocate multiple elements like that, okay? But the problem is that you're going to have some spaces very small and fragmented, basically. That's your fragmented memory. And the thing is, you can remove elements at any time, but it's like, you know, harder to find a place that is free because you don't know when the elements will be destroyed. Do you understand what I mean?
Yeah.
Because, for example, let's say you want to allocate something that is this size, right? You want to find where you can allocate it. Let me just do that. So you're going to first check at the beginning, but this place is too small. Then this space is too small too. This space is too small for all of that. Okay? And that's where you find a place finally that is, for example, there. And you allocate your thing here. But it's like kind of not really optimized, and it's really basically it has to find a free space, and it's taking time. That's why dynamic allocation is like expensive. Am I making sense or?
Yeah.
Okay, I hope. And basically, if you want to allocate dynamically in C++, you're going to use the new keyword. Or like you can also use malloc in C to allocate memory without a type. And like in Java or C# or all of these languages, when you use new, it's basically doing the same thing. It's allocating dynamically. But they have a garbage collector. So, you know, it's like a bit... You don't really have to worry much about the deletion. But in C++, you have to delete. Well, I guess you should use smart pointers. So it's deleting automatically too, in that case. But anyways. So yeah, basically that's how the heap works. But it's like slower. Okay. And another thing is, well, let's return to the array and all of that, okay?
Okay.
So we have vector array list. So this is a linked list. I'm just precising for people that are using other languages. Okay, and array. What is array? STD array.
STD array. It's an array.
Yeah, but how specifically? Like, what's the difference with that and vector and list?
It's a defined number of elements.
Why is that? Isn't dynamic better? So why not doing something dynamic instead of static? Why having a precise amount of elements that you are allocating and not something dynamic?
Because it's more optimized on some cases.
Why is it more optimized? And it's not in some cases, it's always more optimized.
Because we already have in the stack. We already have.
Yeah, that's it. Basically, it's using the stack. Array is using the stack. And it's like basically the same. Array is exactly the same as allocating an array like that. With your elements, right? It's the same, but it's just a templated version of doing that. So that, for example, you have access to some utility functions like the size that you have to redo with that kind of array. Or, for example, you also have iterators, I think. You can have a for each loop with that, which is not the case with a C array, basically. But yeah, with like other languages, you have this kind of arrays too, basically. But yeah, well, I guess. Yeah, I guess it depends. But yeah, okay. So yeah, this is allocated on the stack. And that's why it's very fast to allocate, okay? And what it's doing is basically allocating a bunch of data. So like you have multiple elements of the same type inside your array, right? Okay?
Yeah.
Yeah. And then, since we know the size and all of that, when we are going out of the scope, it's just removing very fast. So now what's std vector?
I don't know.
Okay. So instead, let's just start
It's an arrow.
let's start with something a bit easier.
Yeah.
Let's say we have int that p. Wait, this is a bad p, and we have a new. Hello, new here. Welcome. How are you?
Hello. How are you?
Basically, you can allocate an array, okay, like that, with new this time. What does that mean?
It's using the heap.
Yeah, that's it. It's using the heap. Fine. What are you doing today? Well, basically, right now, talking about memory and like the stack and the heap. Why what? But yeah, basically learning while teaching data structures and algorithms to Azrato. So like understanding. Yeah, it's him. And yeah, going very low level right now. Not as in easy, but as in memory oriented things. Because to explain why some data structures are more optimized than others. So array is like really optimized because it's on the stack, and the stack is very simple. And it's like, yeah, allocating very fast. And then we have the heap that is slower to allocate from. And we have this, for example, we can allocate an array on the heap. But it's like slower because it's like dynamically allocated. I came here searching for Leetcode. Oh, okay. Well, I guess it can also help you because if you want to solve some stuff on Leetcode, you have to know, algorithms and data structures. And that's why we're doing that. And yeah, basically we're going to talk about the difference between vectors, arrays, and lists. And like basically why each container is optimized for different things. So yeah, as we're told, we have our dynamic array, okay?
Yeah.
So what's the difference between that and std array? Or like basically what we had on the right?
I don't know, it's slower.
This is on the stack and this is on the heap. This one is slower, right? This one is faster. But like there is another difference. The difference is that this number right there, it can actually be a variable. So it's dynamic.
Oh.
So for example, I equals 5.
And we can change I later. And it update.
You can basically allocate 5. Okay.
Yeah.
So this is dynamic. This is static.
But if I do I++, it don't update.
It doesn't update because you allocate a bunch of data. But like you can't basically. Okay. Basically on your heap, let's say you have your array. So this is the array. You can't like just increase the size there because you don't know if there is something allocated there or not.
Yeah.
I use Python. I am noob to C++. I know, but not well. But I mean that's alright because we're talking about concepts rather than languages. So it's like the same in Python. It's just behind the hood, and yeah, it's just behind the hood.
Yeah.
So it's something that's going to help too.
But I can use I here.
Hmm?
And I can use a var here.
You can't in C++. You can't.
Oh, okay.
Except if it's context. So if this variable is known at compile time, you can. But if it's not, you can't.
Oh, okay, okay.
So yeah, it does.
I see.
Const exp is compile time. In C though, you can. It's called dynamically length arrays. So DLA, I think. But it's like kind of tricky, and I think there were some problems, and that's why they removed it. But yeah, basically that's it. And basically it was less optimized because of some specificities. Can we dynamically allocate object than allocate heap during runtime dynamic? What? Then allocate heap during runtime. Well, you can allocate. Basically, if you want to allocate objects dynamically, it's basically allocating on the heap directly. So yes, that's using the heap. If you allocate anything dynamically, it's on the heap. And on Python, when you use the new keyword, it's allocating on the heap. So it's there. In Python, basically in object-oriented languages, you have a lot of stuff allocated there. You know, for example, in C#, well, I guess in Python too, right? In Python, let's talk about Python. In Python, you have objects that you can allocate with, well, I guess that there is no new keyword, right? It's just something like that. I don't remember. But yeah, you allocate your object, and basically it's on the heap. Azrolto, can you help me? In Python, do you have the new keyword?
No.
Oh, no, you don't. Because basically you have something like that equals foo, like that, right?
Yeah.
Yes. Oh, yes. Yes, you have the new keyword. But anyways, you have something like that, okay? For objects. And you allocate on the heap. But if you have, for example, an integer, then it's like a primitive. No, we don't use new. Okay. So yeah, it's on the heap. But if you use if you create a primitive like that, like J, it's on the stack. And it's basically like more optimized. And what? I guess that's mostly it. Because, you know, when you do, for example, int I equals J, it's doing a copy. Okay? But if you do foo f2 equals f, then it's not doing a copy. It's like taking the reference, right, towards the same object.
Yeah.
So that's also...
Yeah. And if we edit the original, it edits the FT2.
Well, yeah. If you remove, like, if you deallocate the memory for this one, is like deallocating everywhere because it's like sharing the same memory on the heap, right? So for example, it's allocating that. This one is pointing to the same place. But if we create J, so for example, here, then I equals, it's making a copy, so it's basically creating another memory space and pointing there. Okay. So it's basically the same thing in like languages. In C#, you have classes that are basically on the heap. But then you have struct. And structs are on the stack. That's the difference. So you actually have a difference between classes and structs in C#. But in C, you don't have that. In C, it's the same thing because you, you tell the compiler explicitly when you want to allocate stuff. With like, well, I guess. Well, you decide if you want to do new or not, actually. But anyways, it's like using the same principles behind the hood. And you can allocate an array statically on the stack, or you can do that dynamically on the heap. Okay.
Okay.
And so yeah, this one you can set the size dynamically, but this one you can't. This one is static. Now, std vector, and that's, well, basically a lot of programming languages use the same concept. So you have std vector in C++, but in Python you have it's just a simple list, basically. In Python it's like a list. In C#, I guess it is array list. And basically, you know, you stream daily, I love to learn from you. I don't, sadly, but I'm planning to have a big stream right now. So yeah, you can always see the VOD on my YouTube if you want. And thank you. So you have basically the same concept as std vector. Okay, this is the same stuff.
Yeah.
And the goal is basically to use this dynamically allocated array, but instead of using everything at once, okay, let me create a new schema. So let's say you have your memory, okay?
Yeah.
Are you going to do problems and puzzles? Yeah, that's the plan, yeah. But right now we're talking basically about vectors and, well, very soon about algorithms, because we're going to, you know, we're doing vectors and lists right now. So let's say you allocate, well, okay, you have a std vector. It's going to allocate a bunch of memory, okay? So for example, all of that, it's allocating. So it's taking some time because it's allocating on the heap, right? So it's kind of slow to allocate, okay? But when you create your std vector, it's empty at first, right? Like there are 0 elements.
It's a null element.
Yeah, so let's say now you add 1 element, okay? So you have this new element that is there, okay?
It's a 0.
Well, yeah, it's like the index is 0, but that's your first element, right?
Yeah.
0. And now the size of your vector is 1. And now if you want to add another element at the end, then you can add it basically there, right?
Yeah.
And you can also add a new element there, right?
Yeah.
And basically you can add elements very fast because it's already allocated.
Yeah.
You don't have to allocate something on the heap again because you already have your array that is allocated. It's just that elements are unused and you have some memory that is allocated but that is unused, right? All of the thing in orange after that is unused right now. But it's basically some kind of cache that you can use if you want to insert new elements. Right?
Yeah. Like with the stack.
Yes, but it's fixed. Like it's smaller, and the thing is, the stack is yeah, it's very similar in concept, but the stack is fixed. Okay, let's say it's like 256 megabytes. All of that. Okay, that's a lot, right? You don't really have to worry about it.
Yeah. But
in comparison, like your vector is not going to have to be that big. It's like, for example, maybe going to have 2, 4, 8, for example, 16 elements, or maybe 8, we can say, because, well, it's better to have a multiple of 2, a power of 2, right? Like 2, 4, 8, 16, 32, 64, 128, all of that. So let's say it's allocating for 8 elements maximum. you're going to reach a point where you're going to basically get at the end, right?
Yeah.
And what's happening in that case?
Error.
No.
Oh.
It's actually just removing all of that. And on the heap, it's still the heap, is going to allocate a new memory that is basically double the size of what was there.
Oh.
So instead of 8, it's going to be 16, for example. And it's going to copy your elements, or actually move in C++. But you can see that as a simple copy. For example, in most languages like C# or Python or all of that, it's basically a copy, because you're also copying your objects, right? Well, copying the address of your objects because it's pointers. But yeah, it's basically doing a copy, and yeah, now you have more space for your elements.
Yeah.
Hey. So that's how a vector works. You can also you have a function called reserve to reserve the amount of memory you want if you're planning to have a certain count of elements, for example, if you don't want that to happen, because it's taking time to reallocate and copy everything, right?
Can I reserve like a gigabyte of RAM?
If you do that, it's probably going to allocate on the disk, so it's going to be even slower.
Oh.
Because it's like using behind the hood. How is it called? VRAM, right? You have your VRAM. Because, I talked about the RAM, but you have the VRAM, and it's basically some indirection to virtually allocate. Oops. Virtual allocation. And basically the goal of that is just to basically use the thing that is the fastest possible in priority. But if, for example, the RAM is full, then it's going to use the disk. If the disk is full, then it's going to use Google Drive. It happens to me, because my Google Drive was connected as an external disk, and it was using Google Drive to actually process data, because my deep learning model was just too big, okay? So it's actually, some indirection.
I have a 5 terabyte FTP.
Well, basically, you can use that for your VRAM.
I have 5 terabyte of RAM. Vroom.
But yeah, that's how std vector is working, and ArrayList and Python arrays and most arrays, basically, because it's you allocate once, kind of, and it's very fast to add new elements, to remove them, and it's dynamic. You don't have a fixed size, so it's very useful, right? But now we're going to talk about linked lists, basically. The linked list concept, because the data structure is called the linked list. Do you know what that is?
Yeah, I know.
Okay, so tell me what it is.
Do a little scheme. I will do a little scheme for explain.
Yeah, show me.
This is my first element, and there are a pointer after, which point to the next element.
Yeah, that's it. List. You have pointers, as you said. It's pointing to the next elements. So now, if I have to ask you, is it on the stack or on the heap?
I think it's on the stack. Oh no, it's on it's on stack.
Why is that?
Because you have only one element and a pointer, so you can do it in the stack.
Is that C? It's like a lot of languages. It's working for any language. It's like concepts that are used for every language. So it's like useful to you. For example, this is C++, but this is Java or C#, and this is Python. You know, it's like concepts. And the answer is, well, basically, do you know the size of your lists or not?
No.
So that means, can you allocate it on the stack?
Ah, okay. I see. It's on Heap.
Yeah, that's on the heap, because you don't know the size. Because it's dynamic, right?
Yeah.
So it's on the heap. So let me create the heap. So this is the heap. Okay, now when you create an element, the first element, show me on the heap how it's done.
So I have my first element.
Okay.
It's an and I have my second element, which is a pointer to the next element. Whoops. And this point here, and this point, something like that.
Yeah, that's it. You got it. So the difference between a linked list is basically that a dynamic array, like std vector, is allocating something straight in memory, right?
Yeah.
Like it's continuous. The memory is continuous. But this is not continuous. You could have an element in between. Right?
Yeah.
So now what's the difference algorithmically wise? So okay, let's put some functions maybe. Okay.
Okay.
Let me do that in green. So you have add. Well, let's. Okay, I'm going to use the C++ functions. Okay. Oh,
Okay.
what's that? Yes, please. Oh, thanks. Okay, so you have, for example,
Maybe we can go on this code to do that. So.
No, let's not. Not right now.
Okay.
So, for example, in C++, you have push back for vectors. Okay. Do you know what it's doing?
No.
It's adding an element at the end.
Oh, okay.
At the end, okay. You have pop back, which is...
Remove an element, the last element.
Yeah, you remove the last element. That's it. Then you have...
Push front, something like that.
what? Sorry?
No.
Front? I guess you do have that, but it's not really necessary here. You have insert.
Yeah.
What is that?
To insert a number at an index.
Yeah, that is not necessarily an index, but yeah, inserting an element in the middle of your container, basically.
Yeah.
And you have arrays, that is basically the equivalent. So these two functions actually use iterators in C++. So it's not necessarily an index, okay? An iterator can be an index, but it can be something else. For example, for lists, it's like something else. But
Okay.
yeah, so pushback, popback, insert, erase, and I guess that's mostly it. Okay, we can say. So now, let's say I do pushback on a list. What is it doing? A linked list.
It's adding a pointer to a next element.
To the next element that
you push on the list.
Well, that you allocate, right?
Yeah.
So it's, well, basically the allocation is slow, right?
Yeah.
So this is kind of slow for a linked list. Okay. Right?
Yeah.
Okay. And now if you do, well, basically if you do pushback on an std vector, like here, what is it doing?
Yeah. It's faster because we have already allocated memory.
Yeah, it's already allocated. So it's just, using something that is allocated. So it's like very fast for vectors.
Yeah.
So, can I actually, let me, how can I say, oh, that's right. Let me just move that. Okay. So you have vector, and you have, I suppose, linked lists, right? Like that. Ah. Right. So we just said that so this one is fast, like very fast, right?
Yeah.
And linked list is like slower because dynamic allocation. Well, basically alloc. Well, it's like fast. Like in general, it's like fast. Not necessarily faster. It's faster, but like fast in general. No, pop back. What about that?
I think it's the same.
So let's look at the list. The linked list. What are we doing when we are popping back?
Oof.
Yeah, that's it. So basically you have to deallocate. And it's like calls to the
Free function.
To the operating system to deallocate. So yeah, it's like kind of, well, it's alright. It's not that slow, okay? It's alright. What about the vector? If you want to pop back the last element.
Oh, we just replace it with a null value.
No, you don't even have to replace it. You just stop considering it.
Oh, okay.
Because you're not using these elements, but you don't even have to know what these are, right? Like you're just saying, oh no, instead of having 7 elements, I only have 6 of them now. And that's it. You don't have to do anything else.
Okay.
Because you're just not going to consider that element anymore. That's it. That's all. So it's actually like the same as subtracting an integer. It's like really fast. So this is fast. And this is...
Boom boom.
Yeah. And this is, I guess, fast.
Less fast.
But slower. Right. Once again. And the thing is, for insert and erase, for linked lists, it's actually the same thing, right? Like if you want to erase an element in the middle, then you are going to deallocate and set the pointer to the next element, right?
Yeah.
If you want to insert an element in the middle, then you are going to allocate and just reroute the pointers, right?
Yeah.
So this is kind of the same. So there is a deallocation. Insert is, well, basically there's an allocation. And erase is a deallocation. But basically, it's like O1 because it doesn't, well, algorithmically, it doesn't depend on the amount of elements you have, right?
Yeah.
So everything we saw until now is O1.
Yeah.
Except remember, when we are doubling the size of the std vector, we have to duplicate each element, right?
Yeah.
So that means in this case, it's like ON.
Yeah, because we copy.
Yeah, we copy. So like worst case is actually ON, but average is O1. Worst case ON, because we are going to copy n elements. So yeah, that's nice. Now what about insert in vectors?
I think it's the same. Oh no, because we... Oh. Worst case 01, best case 01, but the average is the... something like ON divided by 2.
Well, you can say that. I guess we don't really... Well, basically in... how is it called?
Because we have to move all the element
Yeah, that's it.
at the right to insert.
Yeah, that's it. If we want to add... If we want to add an element, a new element here, we have to copy the elements after that. Like, to move them, basically. So, yeah, and like, algorithmically, we discard the constants. So you're right in saying that it's like average of ON divided by 2, right?
Yeah.
But since we discard constants, then it's equivalent to just saying it's ON.
Oh, I see.
And for erasing an element,
It's the same because we have to copy all the element back.
yeah, you have to move them to the right. Well, to the left, I mean, in this case. And like removing this element. So yeah, you're right. ON. Yeah. So this is kind of slow. like really slow and slow. Okay. So now, if you look at the complexity, which one is the best container?
It's linked list.
Yeah, that's the best one.
If we use insert and erase.
Yeah, indeed.
If we use
That's it. But as you said, well, basically what? Yeah, the insertion and erasures are like faster, right? But like it's like still 01. So even if allocating on the heap is slower, you know, it's still fast, kind of. But yeah, it's like a really nice container, algorithmically wise. And let's say you don't want to insert elements after that. Like, well, why are vectors more used than linked lists? Because like
we use
linked lists really have like a lot of algorithmic complexity good things, right? It's like 01 everywhere, and like okay, it's like maybe a little bit slower when we insert at the end, but you know, if you want to have 01 everywhere, it's like really good. So yeah, why?
Because it's very complex to use.
What do you mean by that? What if, for example, by default in Python, arrays were using linked list instead of vectors? Like it would be very easy to use, right?
Yeah.
So why not using linked list?
Oh, because we have two elements for one element. We have element and a pointer.
Sorry? An element and a pointer.
Element for one.
Well, I guess I guess we have to talk about memory now. Memory. So every time you insert an element, let's keep that. For vectors, you basically have a constant that is 3 pointers plus n, right? Because you have your amount of, well, basically n times the type of your object, right? Like it's your object. Well, basically n, and you have Whoa. Size of t, right? T is your element, okay? Do you understand that?
Yeah.
Okay.
Yeah. For example, an int is.
Yes, an int is
32.
4 bytes.
32 bits.
32 bits and 4 bytes.
Yeah.
Actually, it depends. It's not necessarily true. Because depending on the computer, basically, you can have an int that is only 2 bytes. You can have that. So it actually depends. So that's why you use, for example, int 42 sometimes.
Oh, I see. Okay.
And now for the list, you have basically some constant at the beginning, like the size of your list, for example, plus n times well, for each element. For each element, what do you have? You have size of t plus the size of your pointer, as you say.
Yeah.
Size of pointer. So yeah, that's actually one con of lists. You're right about that. But there's something else. But that is kind of hard to know. So I'm going to tell you, okay.
Okay.
It's when you use that. Basically, vectors are continuous in memory, right?
Yeah.
Wait, is my stream still working?
Yeah.
Wait, is it?
I see your stream.
Okay. It was disconnected. Oh, love your content, man. +1 follow from me. Thanks. Is that it? Sorry, I just got disconnected quickly, but I'm back. Okay, so this is continuous, right? For vectors. But for lists, for linked lists, it's not continuous. And it's actually a big difference. Like a very big difference. Because remember when I talked before about the RAM and the cache and the processors?
Yeah.
Well, for example, I told you about SIMD, right? That is, you have 16 values potentially, right? But they have to be continuous in memory. Well, do they? And I guess it depends. But basically, for example, the cache, at least, is working that way. What's happening when you want to process a variable is that the area around that variable is put in cache. So let's say you are processing a vector, a std vector, okay? Let's say you are processing this element, the 2.
Yeah.
Then you have all of that data that is put in cache.
Yeah.
And it's basically becoming really, really fast to process. Like really fast. Okay? But now, let's take the example of linked lists. It's not continuous. So if you want to process that element, the data around it is put in cache. So for example, all of that, right?
Yeah.
But then if you want to process this element, the second one, then it's going to have to fetch all of that to put that in cache now, right?
Yeah.
And you're basically going to have some cache misses, cache misses and cache hits, it's called. So I think it's actually explained on the graph. You have a hit there. So if it is in cache, then it's a cache hit and it's optimized. That's what's happening with vectors. But with linked lists, you actually have a cache miss, and you know it has to fetch again to the cache. And basically, if you want to iterate over your vector, it's going to be faster than iterating over your linked list because of that.
Okay.
Yeah, that's it. So that's why you are basically using vectors, because even if you have to copy your elements, right, when inserting an object or, inserting an element or all of that, right? Even if you copy your elements, it's already in cache anyways, so it's like really fast. But with linked list, you have like problems just iterating. Like if you don't want to add an element anymore, like for example, let's say what? Let's say you are in a video game, okay? You have multiple objects. So for example, you have multiple objects and each object has a position, right?
Yeah.
So you can allocate...
Like my player on 0, my monster on 100 or 0.
Yeah, something like that. Basically, your position array can be continuous, like that. And it's going to be... Like, when you are going to go through your entities, it's going to be really fast to get the position of your entities. Like, for example, for rendering or for physics. You can get the position really fast because it's like continuous. And you can have operation in batches. But with linked lists, it's going to be a cache hit every time. And it's going to be, you know, a bit slower when you just go through without adding or removing any object. Because, you know, each frame you have to go through the list of positions, for example. But you don't necessarily have to add an object each frame or remove it each frame. So it's like optimized for going through the list, basically. Going through the container. The collection. And what? And yeah, that's called, basically, yeah, it's called data oriented. And it's like a paradigm, oriented, and it's like opposed to object
Oriented.
Yeah, that's it.
For example, C here.
Yeah. Cocorico.
And in Java.
Yeah, for example.
CPP.
But in C++ you have the choice. And like in C, you can actually have some object-oriented approach, I suppose. Like, it's like paradigms. But do you speak Japanese? Yeah, I do. Hanasemasu yo.
Speak Japanese.
Hi, Nihongo hanaseru. Hanashimasu.
Ganbawa, mina ganbawa.
Domo.
アズルです。よろしくお願いします。
Yoroshiku. But yeah, it's like ways of programming, but you can, you know, it's like not really restricted. I guess in some languages it is, but like, for example, even in Java, you can allocate bytes in a chunk, and I'm sure you can have some stuff like to do it in a data-oriented way. So it's like different ways of programming more than programming languages. Right? Because, for example, in C, you can allocate a lot of objects on the heap, right?
Yeah.
And like have them be individually there. Is your friend Japanese? No, he's not. Not this one, not Azroto. I'm in Japan though.
When did you do when you can do a vlog in Japan?
It's kind of tricky. I maybe want to do that. But yeah, and like basically data oriented is making sure your array is continuous and that you have your cache hits and that you don't have any cache miss. That's the goal. And yeah, that's it. So yeah, we know all of that. Woo! That's great.
Yeah.
So now we can actually do an algorithm. I have a really nice one, but I'm wondering. It was pretty expensive.
The whiteboard is very, very big.
Yeah. Code Forces? A Leetcode problem? Probably a Leetcode problem. I'm just thinking about which one. Because we have the stair climbing one. That is really nice. But it's like more of a recursive thing. Let me think. Well, okay, never mind. We can... should we? Wait. Let me actually search for algorithms that can use a simple array. Oh yeah, I guess we can do... Yeah, okay, two-sum. Let's do two-sum. Well, two-sum is simple, but it's like, you know, to do some Leetcode problem and alternate between all of that. So we have Leetcode. An easy one, I suppose. Yeah, it's easy. Do we have... Yeah, array, I suppose. So we have two-sum. Container with most water. What's that? Let's remove the... Yeah, you don't see that. Oh, this one is like a sliding window. Okay. So yeah, let's have two-sum. Do you know about two-sum?
No. Can you send me the
Yeah.
The link?
So I guess we can do that on Visual Studio Code.
Oh, yeah, it's better. Oh, we have already a Visual Studio Code here.
Wow. So let me just... Can I actually remove this side? Yeah, I guess we can do that. So...
Hey. Oh, I see. Let me put the problem here.
Good. Why is it?
Put my VS code here.
It's so bad. Oh, okay, got it. I just kind of did something really bad. Duplicate, not a reference. That's why. So we have code. Now we have basically that.
You're a very good streamer.
I know. Okay, here we go. So I can zoom in a little if you want. And okay. Wait, it's kind of bad. Okay, here we go. So two-sum. Given an array of integer nums and an integer target, return indices of the two numbers such that they add up to target. Well, I know. Wait. No, this one is actually not good for a simple array. Well, it's using like another container. What is your Leetcode profile? What is it? I wonder. It's progs or something like that. Progs, yeah. I don't have a lot of problems solved. Well, I could have more, I suppose. I'm not like...
I have only one problem to solve.
I do have some Leetcode things solved, but... yeah, like 83, basically. It's not that much. Not that many. Yeah, two-sum is actually kind of tricky. Let me find another problem. Remove element. Because it's going to use a hash map and I don't want that. I want something that is simply using vectors. in place. Oh. Okay, this one is nice actually. Oh, this one is nice. Oh, I solved it already. Yeah.
Okay. Here, here, here.
Oh, it's not. Oh no, never mind, it's good. So remove element.
Given an integer array nums and an integer val, remove all occurrence of val in nums in place.
I guess you didn't want C++, right? I can't change the language. Why is that? Why is that? Can you put the C++ version? The code in Visual Studio Code.
We are already in C++.
Well, no, I mean, Leetcode for me is in C#.
Yeah.
So I want you to put the C++, you know, function in class.
Yeah, I'm in C++. Here.
Yeah, thanks. You. Let's do that.
Maybe we should import something. Yeah, include stdio now.
Anyways, what? Yes. No, you don't need that. No, you don't need that. Because do you know why stdio is for?
Yeah, it's for input and output.
Yeah, but the goal is just to implement a function, right?
Yeah, but I want print to test.
No, you don't. Okay. But then stdio is for C. If you want to have the input and output for C++, it's like iostream.
Oh, but I just want to use printf.
Don't use printf. Use stdcout. Because we're doing C++. You wanted to do C++, so let's do C++. You actually have something called IO forward, IO stream forward, something like that, I think. That is to get the forward declarations of IO stream. So if you want to not have your headers filled with, well, increase the compile time of your program. Anyways. So yeah, the problem. Given an integer array nums and an integer val, remove all occurrences of val in nums in place. The order of the elements may be changed.
What is the in-place algorithm?
What?
What is the in-place algorithm?
In place, it means that you're not going to reallocate your array. And you're going to do that on the memory that is currently being used. So you're not going to create another array, basically.
Okay. So I start with a 4.
The order of the elements may be changed. Then returns the number of elements in nums which are not equal to val. So this one is not really a problem.
Nums.size. Yeah.
What the fuck? Consider the number of elements in nums which are not equal to val be k. To get accepted, you need to do the following things. Change the array nums such that the first k elements of nums contains the elements which are not equal to val. The remaining elements of nums are not important as well as the size of nums. And return k. Okay. Okay, so first tell me, what's the complexity of your algorithm?
I'm going to do an ON.
Yeah, that's it. That's ON. But I'm sure you're going
Where I
to...
get the size?
It's just dot size.
But
Yeah.
it's
It's that. It's a function.
Oh, okay. I see.
Also, I'm just going to do that straight away. You put that inside.
What? Or never?
Well, actually, it depends if you want to. I mean, I guess it depends. I'm just going to put it inside for now, right? Is that fine with you?
Yeah.
Oh, okay.
Yeah, it's fine with me.
Okay. This one is actually tricky. Anyways.
So, if I see, alors, if nums equals val, so I num erase it works or not?
So remember what we said before? Okay, so actually, yeah, okay. No, never mind. Continue. Okay, so basically you want to erase. Erase is taking an iterator, not an index. Okay. You could do that in other languages, though. So I can help you if you want. Okay.
Yeah, help me.
It's like you wanted I, right? So it's basically in C++ is begin plus y plus I.
Oh, okay.
Because begin is the first iterator of the container, and plus I means that, you know, you have an offset of I elements from the beginning. So you have your ith element, I suppose.
And I need to return 0?
Inside the function.
Oh, yeah. Oh, no. Yep. Why I need...
Okay.
Wait, I should... Oh. The number of elements in nums which are not equal to val. Ah.
Wait, what?
I should...
Oh, return 0. Yeah. Count.
Enter.
Can you... I'm going to do something on my OBS. Can you... Okay.
Yeah. Can I? You want me to test? Submit. Oh, wrong answer. Oh. It doesn't work. Why are you mute?
Oh yeah, sorry. Let me think. Yeah, it's not working, and I know why. It's not working. Why is that?
Oh. I think we will do y minus minus.
Yeah, you can do that.
Like Submit.
Okay. So this one is not working. To 0 output expected. Oh yeah, I know. I know.
Oh.
I know. Do I? Wait. do I? This is 2. Oh yeah. Oh no. Wait. Oh wait. Yeah, something's wrong. Yeah, I guess something is wrong though. But wait, is it? Wait, maybe not. Yeah, no, never mind. No, it's alright. If nums equal. Well, I guess you can print them. Try that.
Ah.
I'm going to create the example function. Don't worry about that. Just add your things. Why is it that bad? How can I stop following you?
Yeah. I don't know.
I did it. So we have the solution.
You do.
We have solution that remove elements. So we have this one with, can I insert, okay, int array that is 0, 1, 2, 2, 3, 0, 4, 2. We have array plus, I guess we can do a std array. Oh, but never mind. Size of array divided by size of that. And wait, what else? Plus, well, anyway. Oh yeah, it's not insert. Insert. Wait, I don't remember. Insert. Position. Oh yeah, we have the position. So this is begin. Our back is working too. And we have the value that is 2. Because basically, okay. Well, yeah, I don't. Well, I guess I could explain iterators at a later time. Not really right now. 2. We have that, okay. And we have nums and we have val. Okay, so now if you want to run that. Oh, you didn't print the thing. What did you want to print?
Yeah. Pointer equal. Can printf? Yeah.
No printf. You don't need that.
std. Something like that.
Yeah, std cout. Counter, and yeah, that's it. No.
Oh,
you don't need that. Well, you can. Well, I mean, you're just doing that once, so you can.
I need to print the nums.
Yeah, I guess for that you can. Let me do that.
Let me do it for you.
Okay, you can do it.
You want me to do it?
I mean, you can. I'm interested
I
in
can.
how you would do it. Yeah. No. No.
Oh. Ah. Int element.
Yeah, you can do a for each, a range-based loop.
Oh, it works like Java.
Yeah, that's it. Like it's like the for each in C# too. I think endline is like to add a backline character, but like it's also flushing the buffer, I think. So it's like less optimized than \n, but that's fine. Yeah, you can do that. So yeah, you can run if you want.
Yeah, I need to compile.
Yeah. I don't know if I can see. Oh,
So,
I can see that.
you can see it. G++, G++ theory wall.
Oh, are you doing that?
Oh, test.cpp.
Yeah, because you don't have any.
Oh,
That's
warning.
fine. That's fine. It's just a wrong type. Because it's actually size T.
It works on my.
Hmm?
It works on my computer. It literally works on my computer.
Let me look again. Oh, because... No. It's not working. I got it.
Oh.
Because look at what it's returning. Free. You're returning the wrong value. So it's only showing the free first elements because you are returning free. But what they are asking is to return basically k, which is the amount of elements that are not equal. And you're counting the amount of elements that are equal. Right.
Oh, I need. Oh, okay. Health.
You don't need that. No, come on. Come on.
Yeah.
You're erasing, so the size is changing. That's also why your for loop is still working. Oh, yeah, no, never mind. Yeah, so the current size is indeed correct. Indeed.
So I try to.
Yeah, do that.
Submit.
Run.
Oh yeah, accepted.
Okay.
0 millisecond runtime. Vroom vroom.
Oh, this is it.
It's 100%.
So this is actually not optimized. No, wait.
This is really
no.
optimized.
No, this is not optimized.
This is optimized.
Because basically in Unreal Engine you also have an erase that is faster. That is implemented faster. And basically this is not the optimized version.
Oh, it's ON.
Because you did tell me earlier that, well, you did tell me what is supposed to be the complexity of this algorithm.
Oh, it's ON power 2? ON square?
Well, you told me it was supposed to be ON, right? But it is indeed ON square because erase is ON for std vectors, right?
Yeah.
And you have basically a loop, a for each loop, so this is ON.
But I beat 100% of people.
Yeah, but it's
the best.
So yeah, basically you can optimize that. What can you do?
I try to implement my own erase.
Yeah, you can. How?
I don't know.
How can you be faster than that? Because we explained the mechanism before that, right?
Yeah. Oh, I can do it. I really don't know.
Okay, look at the stream.
Yeah, I look at the stream.
Okay, maybe there's going to be some delay.
Oh, the order of element might be changed.
That's the difference. Because with arrays, it's trying to conserve the order, basically.
Yeah.
And because of that, it's copying, like, and it's being ON, right?
Yeah.
Okay. But now, let me duplicate. Let me go back to Whiteboard.
Whiteboard.
Boop. So if we check, we have all of that. So in std vector, we saw that erase was on, right?
Yeah.
What other function is there that is not on, that is removing an element?
Up back.
Yeah, pop back. That's it. It's O1. It's really fast, right? So can you find a way to use pop back instead of erase?
And it takes no argument. I see. We need to put the vowels at the end.
Tell me again.
We need to put a val at the end of name.
Val? Oh, well, just do your thing and you're going to see.
I think I need to put all the Q at the end of nums and after erase.
Just modify the algorithm. You
I
can.
think I can just pop back. Why? I can't. Yeah.
No, you can't, because it's not at the end.
Yeah.
Pop back
But-
is just removing the last element.
Oh, I can do it. I think I have an other way to do it. Like with... oh no, I can create another... oh, I changed the order of elements. Can you help me a little bit?
I don't know if I can help you more. Well, first, we just said that we replaced erase by puff back, right?
Yeah.
So we have something like that, right?
Yeah, but oh, we put...
What's the problem right now if you do that?
we will delete some numbers that aren't val.
Yeah, that is what, sorry?
That are that aren't val.
Yeah, that's not. Yeah, that's it. We are removing the last number of the array,
Yeah.
but it's not necessarily val, right?
Yeah.
So this is bad, and it's not removing the val, the current value, right?
Yeah.
So if you want to keep that last value, what can you do? you want to remove the current one and remove the last one. Well, I can't say. Well, you want to remove the current one and save the last one.
That's a good question.
It's one line. One line.
It's one line. I need to insert it back.
No. Well, in a way, I guess you can. Okay, so don't forget that you can change the order of the elements.
Oh, I put back only val. So val must be at the end. Ah, I need to swap. Okay.
Yeah, that's it. And actually, you don't even need to swap. Because we don't... Well, the last element doesn't matter, right? So yeah. If you want the last element... No, if you want the last element, it's back.
Ah, okay.
And that's it.
Not really. I can just do something like that.
So, Asbreto, just something.
Yeah.
You want to set the last element, right? You want to swap, basically,
Yeah.
right?
Yeah.
But we are removing that element afterwards, right?
Yes, but
So yeah, we actually don't care. It's just that. That's just that. And this one is 01.
That it's work.
And it's working. And now it's
Oh.
faster. And now it's like ON instead of ON2. Well
Funny.
done.
Yeah, I always. Oh, I can analyze. You can analyze complexity one per day.
And here it is. 100%. I think before we were like 97, right? Something like that.
No, we already are 100.
100. Okay,
We
never
are.
mind. But yeah, now it's faster basically. I don't understand why it's like it was why it was good before that. But yeah, that's it. And I think this problem is like it's really a good problem, right, for vectors.
Yeah, but it uses more RAM.
More what?
More RAM.
More RAM. Why is that more RAM?
I don't know. I only bet 5% of people with memory.
What?
Usage.
What memory usage?
Oh. What's? Huh?
What?
Oh no. Okay. Leetcode is
Oh, that. Yeah. No. Don't worry about that. It's nothing. It's kind of because you're just doing everything in place, right? And you basically have one int and one size t. That's it. I mean, it doesn't matter really. It's like sometimes Leetcode is kind of saying weird things, but that's fine. So yeah, this is vectors, right?
Yeah.
This was vectors. That's good. Now I guess we can have a linked list and double linked list. Do you know the difference between a linked list and a double linked list?
No.
Okay, I'm just going to go back very quickly on Whiteboard.
Oh, it's in it works also in the back side.
Yeah, that's it.
It
So
was in reverse too. Okay.
I'm just going to show. So this is a forward linked list in C++, and
Yeah.
a double linked list or just std list in C++ is the same but with backlinks. So the question is,
Okay.
why is that?
Yeah.
Why do you have a list that can go both ways? Well, that has pointers both ways.
If we need to go backwards.
Yeah, that's it. So for example, if you want to remove the second element from the end, you can do that very fast, right? With a double linked list. But if you only had a one-way list, a forward list, then the second element before the end could be like really long, right?
Yeah.
So yeah. So like a forward list is actually fine most of the time. And another problem actually is when you want to remove an... Okay, so let's say you have a list, okay? Like that.
Yeah.
A forward list. Let's say you want to remove this node. What do you do?
I do a for loop until I get the node and I erase it.
Okay, you erase it. What then?
I change the pointer of the previous element to the,
So this one
the next element.
to this one, right?
Yeah.
But you just told me modifying the pointer of the previous element. So you need a backlink.
Oh, okay.
So you know, in that case, basically, if you want to remove an element from an iterator, if it's a double linked list, you can. If it's a forward linked list, you need the previous iterator to do that.
Yeah.
So yeah, that's a difference that you have to be careful about if you want to remove an element. So like if you simply want to remove a node from a list, then, you know, a double linked list is nice. Okay. Oh wait, did I show? Oh, I didn't show that. Oh wait, I did?
Yeah, you did.
Yeah, I did. That's fine. So, now we have double linked list and we have linked list. Add to what the? Oh. You're given to an empty linked list representing. Yeah, I guess we can do that. But there's like nothing really interesting there. Oh, this one is really nice. Oh yeah, this one is nice. Wait, it's actually the same. No, okay, this is nice. Yeah, this is nice. Because it's actually using things that only lists can do.
Can you send me the link?
Yeah. This one.
Yeah. Bang.
Okay. So yeah, basically...
Merge two sorted lists.
Yeah, so you have the heads of two sorted linked lists, this one and list 2. Right? The red and the purple one. Merge the two lists into one sorted list, this one. The list should be made by splicing together the nodes of the first two lists. So basically, you don't want to allocate something new, okay? And if you were to merge elements of a std vector, in that case, what would happen? Basically, either you would allocate a new array, either you would, copy and move elements, right? And like it will be very difficult with a std vector for this problem. right?
You're yeah.
But with lists, it's actually quite straightforward. So let's do that. Yeah, this one is like a good way to understand what a list is good for. So let's create a new file.
I create the file. Yeah,
Okay.
I create the new file.
Can you rename?
Merge the-
Yeah, can you rename the files
Merge.
maybe? Oh, merge. Oh, yeah. Didn't see that.
Yeah.
Okay. So
Help me.
I'm going to
Oh.
have that. Yeah, okay. No, that's fine.
Okay.
So this is a pointer towards the next node.
So I need to. Can you do a test function for me?
Yeah, I'm gonna do it.
No.
So we have
First,
that.
I need to do a new list node.
Val. Okay.
Are you here?
Hey, I'm here. No, you don't have a new. You don't have new. You don't have dynamic allocations here. Because you're supposed to use the nodes that are there. I guess I can. Yeah, you can't. You're going to return like one of these values basically.
Okay. I need. Okay.
I guess I can. For F1. Well, I guess if I just take that, I can do 1. Wait, this is next.
Oh, I don't.
4. I guess I could just have a list though. So std, let's remove that because I don't want to put the amount of elements. 1, 2, 4. Yeah, this is good. Right. 1, 3, 4. Yeah. So yeah, my goal basically as the one that is doing the tests is to have the easiest shape to modify to be able to do the tests. So now that I have a simple array, like it's really simple to modify, right, and to understand, I'm going to convert that into this. So that means I'm going to allocate dynamically. It's not considering if this or null, but that's fine. Okay. Okay, I kind of want to show you thing too. Count. Yeah, you can do that. Okay.
I have an idea of a drinking game with Leetcode.
Every time I'm removing your code, you drink.
Every time I submit and it's wrong, I drink.
Left. So this is basically the size, well, the amount of elements of left, but it's kind of, you know, weird in C++ and in C. So let's say we have that. We start at 1. Yes. L. Well, L. Okay, that should be fine.
I have alcohol on my in my fridge.
Are you stuck or?
No, yeah, I'm stuck. Yeah.
You're stuck? Yeah.
Yeah, I'm stuck.
Yeah. So let's do this. Let's see that together.
I'm waiting here.
Yeah. Okay. So, what do you not understand?
I want to count a number. I want to do my count function.
You can't. You can't do that.
No.
Because, well,
Okay.
you basically you can, but it's going to be
Yeah.
ON.
On.
You don't want that.
The final would be on. Okay.
So yeah, you can't do that.
While loop.
Yeah, that's it.
Yeah.
You got it.
While at least 2.
Because basically from a node, you don't know the size, but you know the next element. And basically the goal is to continue to the next element until it's null.
List 2. List 2 dot next. Dot next. Please.
But no,
Okay.
that's an arrow because it's a pointer.
Okay.
So basically, an arrow is equivalent to dereferencing your pointer, so getting to the element, and then doing the
Yeah.
dots next. But you have a shortcut, and it's just an arrow. I guess in C# and Java and all of that, it's just dot, right? But in C++, you can actually overload. Basically, this is an operator, and you can overload that for classes. So that's why, for example, you can have std unique ptr pointer, right? And then you can use the arrow, right?
Yeah.
Because if you do dot, basically it's using, well, it's accessing the functions and the data from unique pointer. So you can actually use that and, for example, have what? What function is there? I guess you have the destructor, but does nothing much. But yeah, you can do that from unique pointer. But if you want to access the int, or in this case, I suppose this node, then you can overload this operator and access the val directly.
What are you doing on my computer?
Nothing.
Research all references. Cancel, please.
It's not me.
Yeah.
So
I'm a Java man, you know.
I saw that.
I will try to do it.
So is that null?
Oh.
That is it null?
That's...
What? Well, I'll continue.
Okay.
Continue.
So I check if list one. Oh. Oh. I do that. Can I?
I'm actually realizing that to output I just need to do the same as you. So I'm going to wait. What are you doing? What are you doing?
Okay, so it works. Okay, I see. No, yeah.
Uh-huh.
You know.
I don't.
We need to. So if last one dot val.
So is your problem the pointers?
Not really.
Okay.
List two. The list two val.
Mhm.
So I list one dot next. If list one dot val. If list two dot next equal list two. Help me, Mr. Prog.
Okay. Do you wanna do this problem on whiteboard first?
I don't know. Maybe we can.
Yeah, I think it's going to be better to explain what's happening. So, okay, this is fine. So we're here. So, okay, follow me.
Yeah, I'm. Yeah.
2, 4,
Where are you?
left.
Ah, you are here. Yeah, I found you.
Yep, you did. Okay, so the final list is 1, 1, 2, 3, 4, 4. Right. So if you want, okay, so how do you sort that efficiently? You don't
Okay.
have to consider it being a list. You can use a vector, you can use anything, okay?
So I check every value. So we have list 1 and list 2.
Mhm.
If I check a value, and if this value in list 2 is
Smaller. Yeah, basically you
smaller, yeah.
take, for example, this value because it is smaller or equal to the other one, right? So what do you do
yeah,
then?
If it's smaller, I change the next. Oh, I need to know. Oh, wait. I need to know which one is smaller at start.
Yeah, at the start,
In
which
which
one is
list?
smaller? So let's actually change things a little to make it easier, I suppose.
Yeah.
Let's remove elements that are equal.
Yeah. Let's put 3 here, not
Wait.
3.
Can you remove, please? Thanks. 3. Wait. I wanted to put that in blue. 3.
in this.
7. 9. Okay. So yeah, you verify, like you check the element that is smaller, right?
Yeah.
Between the two of them, right?
Yeah.
And basically in this one is 1. So you take 1. And
we
then
don't do anything.
Well, you take 1, right?
Yeah.
You have 1 somewhere.
Yeah.
What do you do then after that?
I go here. And I check this with this. You know, I do this check.
Yeah, that's it. You check
And
3 and 5.
I realize.
Mhm.
So I put 3. I let you put in
blue.
Yeah.
Remove the white, please. Yeah.
Yeah, I remove it.
Oh. Yeah, that's it. 3. Then.
And after I go next here in list 2.
Okay.
I go next in list 2.
And then?
And I check these 2.
Yeah, 5 and 7.
And I see 5 is smaller than 7.
Yeah.
So I put 5.
5 then. What is it?
What did you say?
Yeah, continue.
Okay. And I go next in list 1 and I do this check between 2. These 2.
Yeah, 7 and 10. So this one is?
7.
Yeah. And then?
And after
which one?
I go for 1. And then I check these 2 and it's 9.
Yeah.
And here there is null. And I check if there is null or not in here.
Mm-hmm.
And I put this.
Yeah, I suppose then you put that. Then, because there's null, I suppose. So yeah, I just wanted to show that it wasn't always, alternated. But yeah, that's it. You got it. So now you have to do that in code.
Yeah.
So before that, I removed one line you wrote, right? But I removed it because you did a new. Okay. You can put a variable. So for example, we did see we had an orange and a blue list, right?
Yeah.
Let's have, for example, well, list 1 current and list 2
okay, I
current.
see.
Do you understand? Yeah.
Yeah, I see where,
Okay.
where we are going. Can I do a new list or not?
You can't create a new one.
Okay, I can create a new one. I only
You can't
need
allocate it
merge.
with new. You can't allocate it with new.
It said in the exercise?
What?
It said in the exercise?
What? Sized?
It said.
Inside?
Yeah.
What do you
Return
mean?
the list made by splitting together the node.
Yeah.
Yeah.
It should be spliced
there's
together.
no int. Oh.
So no new. But you can do that. This is not a new list. Okay? Because this is a pointer, right?
Yeah, yeah.
And you can also do that. Right?
Yeah. So, if list 1 current val
I'm
is
going to
inferior than
help you.
list 2. Okay.
Returned that. Okay.
List
Now we're
2.
going to return that.
Dot val. Val. And else. So here I need to return. Oh, okay. I don't. Okay, I see. So.
Actually.
I don't know what to do. Help me, Mr. Proxy.
Return as current. Okay, so yeah, just at the beginning, you told me that you wanted to compare the the first elements of each list, right? So just like what you Control Z, undo. So you have that, right?
Yeah.
So the first goal is to know what we are going to return, okay?
Yeah.
Because right now it's null. And we don't want to return null. So what is the first node we want to return?
Return node equal list 1 current. And
yeah, indeed, because this one is less.
Equal list 2 current.
Yeah, that's it. And it's going to help a lot. So now...
But we need to have a while.
Wait, no.
No.
Not now. Now we're just going to have that, basically. And now the goal is... Basically... Now we are going to have the while. Wait. Well, yeah, I suppose you can do that. So, okay. So now that you added the first element, now that you have the first element, I mean, what are you going to compare?
The next. We are going to compare the next.
Yeah. So, in this case, if list 1 current is less than list 2 current, well, the value, then what are you going to compare? Like just the next one after that, if this is the case.
Oh, I see. So I need to compare here. I need to compare with list one next and list two current. List one current next and list one current.
Yeah, that's it. So write the condition, but we can modify. Or the condition of whatever you want. Yeah, you go do what you were going to do. That's fine.
List one current equal list one current dot next.
Yeah. And yeah, basically, that's why I called them current, right? Because they are going to be pointers that move through the list, right? And then here,
list two current equal list two current dot next.
yeah, that's it. So now basically you have the main logic in your loop, right? But don't put that in your loop, I suppose. Well, I guess you can have multiple things, but I guess it would add more complexity if you put that in the loop. So let's just have the loop here.
I have a question. It works if we put it in loop, this or not?
Basically, you have to add an extra condition to verify if the thing is null or not. So we just continue, and basically it's like easier to see things like that. So that's why I'm doing it that way. So yeah, what is going to be your loop now? Because you have a while, right? What's the condition?
While list one current
So late.
is not null and list two current is not null.
Yeah, that's it.
List one current not pointer and list two current null pointer.
Okay. Okay.
Oh.
As you want. Okay. So yeah, I guess we can do it your way. No. Yeah. Okay. So then, what are going to be your conditions? Well, what are you going to put inside? I mean, je comprends pas ce que tu fais. C'est trop compliqué. Hey, Nicolas. It's just a list.
If list one current the equal null pointer, so
it is not null pointer because you just verified it with the while. So you know it's not going to be null. This is end.
Yeah.
So both are going to not be null. No, I suggest you to keep that. Oh wait, actually, yeah, I suggest you to keep that. Wow. Yeah, I suggest you to keep that for optimization.
I hate you.
I love you. So, but basically that's what we did before, right? Because you were going to overcomplexify anyways. So before, well, most cases are when it's not null, right?
Yeah.
So what are we doing in this case when neither are null?
We are going to do this.
Yeah, that's it.
Something like.
That's it. Actually, that's not it. That's not it.
Yeah, I know.
Yeah.
I know.
There's still something wrong.
Yeah, I know.
Return. No, not return. You're in a function and a loop. Oh, return that. Yeah.
No, that doesn't work. I hate proxy.
Thanks. I love you too.
I love you too.
I love your pain.
That's a really good question.
Haha.
What? You're very kind. No, you're not kind.
So basically, do you want
You're mean.
to access the first node that you're going to return every time?
No.
No.
It's a bad idea.
Yeah, that's it. So you're just going to use that.
Yeah, but how? I need 2 current.
No, you don't.
What could be wrong?
You don't really.
I see. Here.
Wrong place.
Oh, yeah. You're right.
Yeah, that's it. You're going to set the next node after the current one.
And after that, return node current equal return node dot next.
Yeah, that's it. Yeah, that's it. Okay, so now it's supposed to work until the end, but towards the end there's going to be a problem, right? Because one list is not going to be finished.
Yeah.
So... Okay.
Let me write some code, Mr. Proxy.
Yeah, do it.
List one current equal null paid here. So
Baited.
Oops. So I do return current node. I just take this. A while.
Yeah. What are you doing?
List.
I'm going to remove your if, okay.
Yeah. List 2 current equal don't equal null paid here.
Yeah, well, it's not null Peter.
Not null paid here. And I just do heap and I add this. Yeah, and I duplicate this. To do
Wait.
this.
Wait. Yeah.
Wait. Yeah.
Yeah, that's it.
And does that work?
Oh wait, I
Okay.
didn't. I didn't finish. I suppose I'm not deleting anything, but that's fine, right? It's not really safe, but yeah, well, safe. It doesn't really matter to have memory leaks for that.
Safe is for loser, you know.
Yeah.
Memory leaks is
So
a
we have-
life.
Yes. And yeah, what I wanted to do is basically the same as what you were doing, actually. So I'm just going to copy what you did. New node. Well, this is not null. Then we have that equals next. Then we have std cout val. Something like that. Wait. We don't have the IO stream. Here we go. Where is that? I can't see. Oh, there. Can you run?
Yeah, I can run.
Run!
G++.
Do it!
Do it! Dot wall. Dot. Oh, merge dot cpp. Oh.
Haha.
some
With
error.
declaration. Yeah, okay. I can remove that. Okay. Do it again.
We have error and not for the same thing. It's not.
Yeah, that's my fault. Okay, do it again.
We have some warning, but it's not.
You can do it again if you want. I solved that. Oh, actually, wait, what's that?
Oh.
Multi-character constant. Oh, I'm stupid.
Progress on some warning.
Okay, you can do it again.
Oh. Yeah, no warning.
Yay. My bad. Oh yeah, this is because of. Wait, this was wrong. But I plus val l next. Oh yeah, I'm kind of stupid.
Segmentation fault.
Wait. I know why, but
That's very funny.
Yeah, we do love that. Let me think about how to do that, because we only have a forward list, so it's basically we want it. So let's say we have equal new that. Which then we have or equals that, and we can have if left node not ptr.
That's the best moment of the stream.
I mean, it was going to happen.
Okay. That was very funny.
Now I know. Oh, I mean, it's not going to work. Oh, I hate that.
I think that can do a good clip.
Wait. Okay, but then the problem is there. So if L is not null, yeah, I'm doing something kind of ugly, but that's fine. We have L equals L next.
Oh, you do a new node. Oh.
Ew.
Probably.
I mean,
That's
yeah, I'm
bad.
creating. It's
Yeah.
not bad. It's because of you. So if it is null, we create and we go to the next. If it's not, then let's just say it's that. That should be fine. And if it is null, then we also have that. And that should be fine.
Okay.
No.
No.
No, I just have to update now for the right one. Okay, that should be alright.
Okay. Compile time.
Oh, no, that's not fine. I forgot to remove that.
Oh.
Okay.
And it has some issue.
I do it again.
No. Say, yeah.
1, 1,
Have
4.
some
Uh,
issue.
so we have
Why?
1, 2, 4, 1, 3, 4. Is it? Let me actually print print my own nodes, so I can.
Yeah.
Basically, this is a function. For those that don't understand. Node. Okay. And I'm going to print the left node. I'm going to print the right node, and I'm going to print the new node. Okay, do it again.
Okay. G++ merge. Oh, it
1, 2, 4, 1, 2, 4. 1, 2, 4. So, okay.
1, 1, 4.
So yeah, there is a little problem. Left. Oh yeah, because this
But
one
where?
is right. Okay, do it again.
Okay. G++ merge.
1, 2, 4, 1, 3, 4. So this is working. So my inputs are correct.
But why my...
So print is correct,
So
but
it's
yeah,
my fault?
yours is not correct.
Let me try to put it in Leetcode, you know?
So I mean, the beginning is kind of okay, right?
Submit.
You did submit?
Yeah. No, it works. Okay. So it works.
It works?
Okay.
Or not?
No, it doesn't work.
Oh, it doesn't work.
So yeah, it's...
Yes.
So I need to put
Problem.
my problem.
Yeah. You did.
Where I have some issue. Can you help me to find?
So let's divide your code into multiple parts, right? So first,
Yeah.
is the first element correct? Is the first node correct?
The first node is correct. It's 1.
Yeah,
So-
this is correct. So this is correct.
Yeah. Correct.
Slash.
Let
Yeah.
me. Yeah. I'm a Python developer, you know.
Yeah, I know.
Correct.
So
This
then
one?
we have that. Yeah.
No.
Maybe
There
not.
is a problem here.
Maybe there is
Maybe
one.
not. Did you see the problem?
Because
I see it.
current. Oh. And then we also have that. Look at that. Never mind. Yeah, okay. 1, 1,
Yeah.
2, 3, 4, 4. No, it's working. It's working.
Yeah.
It's the same.
Yeah, I've seen it.
Hey,
Did you have seen it?
I didn't see it.
Oh yeah. I found it by
So, yeah.
myself.
And
submit.
this is-
runtime error.
Oh, where?
On Leetcode I have a runtime error. Line 9 chart. Line 9? Ah!
Oh, yeah, I know.
I can put a comment.
Yeah, I know.
Submit.
Because it's when it's null, basically.
Eh?
When you don't have any element.
Ah, where you don't have any element. Ah. Let me. Oh, I see.
No, you can. You can. No. Yeah.
There?
Yeah.
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 Return. So,
Ah bah ça, Richard.
not right there.
Why is that?
If list one. equal null ptr and list2 equal null ptr, so return null ptr.
You can do that.
You can. I can return.
But then what if there is one that is null and one that is not null?
Oh, I see. If list1 equal null ptr, so return list2.
Yeah. And what if it's the opposite?
If list2 equal null ptr, so return. Let's stop.
Yeah, that's it. And you actually don't need the end, right? Because if both are null, then it's just going through the first if.
Submit.
Run.
Compile error. Oh. I put the main. Oh, I see.
Okay, so this is good. The run is working and the submit is not working. Oh, there's a problem actually.
Oh, wrong answer.
Yeah,
Why?
for one. You can click on use test case to get that on your test case thing. Minus 9, 3, 5, 7. Oh,
Why there's an issue with the 5? I don't understand why. And we have 7. That's weird.
7. It's skipping one.
Maybe, yeah, it's skipping the first element. Why I am skipping the first element? So here it's correct. Let's say, yeah.
Here. Again. Yeah, because we modify the current.
Yeah.
Yeah.
You're too smart for me.
No, I just copied your technique to find the problem earlier. Because, yeah, you do have to...
Accepted!
Yay.
Yeah.
Yay.
It beats 100%.
And you have... Yay, well played.
0 minutes gone.
Yeah. And you have 0 allocations. Right?
Yeah.
And you have 0 copy too. You're not copying any value, right? So it's like... let's say we have... can you remove your selection, please?
Yeah.
Let's say list 1 has n elements. List 2 has m elements. Then the complexity, algorithmic runtime complexity is O n plus m. Because you go through each element once, right?
Yeah, so but it's O(n).
N plus m. Because it's not a constant, right?
Oh, it's 2n, okay.
Yeah. It's 2 different n's, if you want. And you don't have any allocations. If you were going to do the C++ one, you would have 1 allocation for a new array, or you would have some copies, right?
Yeah.
So yeah, that's good. That's why you use lists. That's in these kind of things, right? These conditions.
This code is a little bit ugly, to be honest.
Well, the thing is, inside your while, for example, you could add like some conditions and stuff, but I think like if-wise, condition-wise, it's kind of optimized. So I think that's fine. I don't know if it's that... I guess you could create like functions to go through the next one, but nah, I think that's fine. Yeah, I mean, I guess you could split your code into like 3 parts, right? The initialization, the middle, and the end. And put that in different functions, potentially, but that's it. So yeah, we did the list, woo! So yeah, do you see... What?
Iter 1 error, class solution. Don't have any member match to list.
What?
Why?
What is
I have an error. Oh, I don't have an error anymore.
Hey.
Can you maybe find another problem? The last one?
The last one?
Yeah.
Okay, just one? Yeah, I guess it's like midnight, past midnight.
Yeah, and it's time for me to... It's soon time of tea, you know? It's soon tea time.
Tea time.
Tea time.
Well, I guess the thing is, we did see like low-level stuff, we did see vectors, we did see lists. Basically, we have, well, either we look at a new data structure and then we do a problem based on that. Either we stop here, I suppose. So maybe we can do... I mean, there is always trees, right? But I guess I'd like to stay on simple arrays because, you know, like it could be a nice VOD thing, basically.
Yeah.
Like it would be split. But yeah, if we want to search about... Oh, I guess you have something called an unrolled list. I guess you have 3 lists.
What is this?
Oh yeah, you have 3 lists and unrolled lists. So it's basically combining the 2 of them. So let me show you. Let's create a new file.
You can create a new file.
Yeah.
I think.
So unrolled list.
I'm hungry.
Here we go. So basically an unrolled list is a list of vectors.
Ah.
Do you see the point?
Yeah, it's combined the pros of 2.
Yeah, basically, if you want to insert or remove an element in the middle, it's faster than just a simple std vector because you're splitting like your huge vector into multiple elements, multiple small vector. Right. Right?
Right.
And at the same time, it's continuous for multiple integers. Right? Because you have multiple arrays, but like std vectors, which are continuous. Right?
Right.
Yeah, that's it. That's it. There's nothing much about it. You don't really have to, you know.
Hi.
Other than that, you have also something called free lists that are really nice. Okay. Let me... It's kind of complicated. Basically, you can say that, well, you saw the concept with lists, right?
Yeah.
Basically, you have a node, and that points to the next one, right? But then what you can do is actually, well, for example, in the previous example, I instantiated a lot of lists with new, right?
Yeah.
But what you can do is actually allocate all of that.
We do what we want to do.
Yeah. Basically, you can do something like that, right? And having multiple nodes, one after another, right?
Yeah.
Okay. So it's continuous in this case, right?
Yeah.
But the thing is, if you want to delete a node, you can't really do that, right? Because you are allocating an array, so you have to deallocate the whole array, right? If you want to to deallocate one element, right? Well, deallocate. If you want to delete an element, because, you know, your nodes have, let's say it's a class, okay?
Yeah.
Your class has a constructor, but also a destructor, right?
Yeah.
Default. And potentially you don't have an int, but you can have, you know, whatever class you want. And you want the destructor of this class to be called, right? When you're destroying an element, right?
You're right.
So, cout. Ooh. Something like that. And we have... Ooh. And we have... I suppose that, okay? I suppose it's not really... Okay, let's just do that, okay?
Okay.
So when you erase a node, you want the destructor to be called, okay?
Yeah.
And you want to be able to destroy an element of this array without destroying the whole array. That's the goal. I'm going to tell you some secrets, okay?
Yeah.
New is not to allocate memory.
Oh.
Oh. What does that mean? Basically,
Yeah, what does that mean?
New, the goal of new is to call the constructor.
Yeah. Hello, constructor. Moshi moshi.
What do you mean? What did you say?
I constructor desu. Moshi moshi.
Yes.
Yeah, you call the constructor.
Yeah, you call the constructor with new.
Moshi moshi constructor desu.
Hello. Who's there?
Hello.
C'est dehors.
Constructor desu. It's a constructor.
But yeah, basically right now it is allocating, but this is not the goal of new. In C, you have a function that is called... Well, basically in C, you don't have constructors or destructors. Okay? So that's why you don't have a new in C. Instead, what you have in C is something called malloc for memory allocation. And this is basically malloc. And you allocate your bytes. So let's say you want 10 elements. You allocate 10 times the size of your structure, basically your class, right?
Yeah, and there are one error.
Yeah, because in C it's fine. In C++ you have to cast.
Oh, I see. C better.
Okay, so this is basically your allocated memory, right? But you have a problem with that. Well, you have a problem.
Oh.
Basically, you have allocated memory, you have some memory, but you don't have you don't have what? Well, you haven't called any constructor, right?
Yeah.
So what we can do is, for example, let me think. Well, basically, free lm. Oh. Yeah, I guess I can put that in full screen.
And zoom a little bit.
Yeah. Okay. A bit less. Okay.
A bit more on mobile, it's really hard to read.
Oh. Is it better?
Yeah, it's better.
Yeah, okay. Oh. So this is allocating 10 elements continuously on the heap, and it's calling constructors for each element.
Yeah.
This is allocating for 10 elements, but it's not calling the constructor. And this is actually useful for std vector too, because std vector, I don't know if you remember that, but we said that, let me go back. Oh, I can't. No. Oh,
You
wait.
can go back.
Oh, this one? Can you see? No, you can't. Whiteboard. It's not working. Oh, it is. So yeah, whiteboard. We did say that... Oh. That you were reserving elements with vectors. You reserve like 16 elements and you add elements to the vector, but it's actually just using the memory that is already allocated, right?
Yeah.
And the constructor is called only when you add a new element, right? But not when you allocate. So this is basically the same thing. Why the uncut? Wait, what? How?
Because then,
Oh, in the terminal. Okay.
yeah.
So yeah, you can do the same. Basically, let's say you want to add another element. Then you can get one element that has been allocated. So like allocated lm.
Yeah.
And you can actually do something that is called a placement new. And this is basically, I don't really remember the syntax, but you need the type because you're calling the constructor. And is it something? Maybe it's that, yeah. Because you can also put arguments inside. So basically, new node. Let's say the next pointer is null. We put null inside. And you're basically saying, telling the new keyword that you want to call the constructor of this node on that memory. Is that fine? Do you understand?
Not really.
Basically, okay. We can do something a little easier. So, allocated element.
Yeah.
So we are creating, well, we are allocating a new element, okay?
Yeah, so, and we haven't called the constructor.
Yeah, and now
And
we call
need
the
to
constructor.
call the... Yeah. Moshi moshi constructor des.
So this is constructed elements.
Yeah.
Then we can Well, basically call the destructor when we want to destroy this element.
Yeah.
And this is not by good. Well, usually you call delete to deallocate an element, right?
But we need first to call the destructor.
Well, basically we are not deallocating, so we can just call the destructor.
And after deallocate.
What is it? Yes, not, I suppose. Right, the destructor. And then we can indeed deallocate. And in this case, we allocated with free. So we have to deallocate. Well, no, we allocated with malloc, sorry. So we have to deallocate with free.
I want to break free.
So this is it. Okay.
Okay.
And basically,
understand.
if you run that, if you compile and run.
You can. You want me to compile and run?
Yes.
Oh.
Because I don't want to go find your functions. Well, your commands.
I just use G++. Oh, there are one issue.
Oh, what is that? I can't see.
Return.
I can't see your terminal. Oh yeah, I suppose.
Oh, you can.
Oh, output. I just see your nyancat.
Oh, it's good. Yeah, you have forgotten to do return 0.
How can you share me?
You scroll down. You need to scroll down.
I can't scroll down more than that.
You delete the terminal.
Hey, you won.
And I reopen a new terminal. Which is in read only for you, because I don't know.
Oh no.
I knew. You can destroy my Arch Linux system. If I wrote something, did you see me in the terminal?
Try again? Oh, yeah, I can see.
Okay, you can see.
Yeah.
/ unrolled list. Woo!
Phew. So we just have list node. Oh yeah, because we wait. What? Oh, can you compile again? Yeah, okay, because you just run. You didn't compile it. Compile it again, please.
Yeah, I compile it and I run it.
Because now I added the constructor, right? So you have the constructor and then you have the destructor. Constructor, destructor. Right?
Yeah.
Okay, so do you understand that?
Yeah.
Okay.
First allocate memory, then initiate, then destroy, then deallocate.
Yeah. So now the thing is you can, allocate that continuously in an array. So there, right?
Yeah. And then
you can basically allocate, well, you can construct, each element individually, right?
Yeah.
Like that. The thing is, what you can do, there is something called a free list, and you can basically have a list inside that vector. Okay, so it's kind of an advanced concept. What's that? Okay. So basically, let's consider that every element is constructed. Okay. So we have nb elements equals 10. Right?
Yeah. Did you know that I like the onion fritalune?
The onion fritalune. Yeah, I guess. Oh. I guess I can do that. Right? Yeah.
You can do it, Mr. Proxy.
So this is I. So right now we are constructing every element of this, of that is allocated basically. Okay. Right.
Right.
So basically, what we are doing is implementing a heap. Remember when I told you about the stack and the heap, right?
Yeah, I remember.
Well, it's not really a heap, but it's optimized. We are doing something like that. And let's say we want to remove an element in the middle, okay?
Yeah.
That means, for example, we can do, call, for example, free, destructor. And this is this is calling the destructor, right? This is destructing an element, right?
Yeah.
But then if we want to allocate a new element, then what we want to do is allocate there. Do you understand? I don't know if you... this is... Yeah,
okay, we...
Basically...
And we destroy it, okay.
Basically, the goal is to be able to create new list nodes or new objects. It doesn't have to be a list node. The goal is to allocate new list nodes and like rather construct them, because I told you that allocating memory was slow, right?
Yeah.
Allocating memory is slow. So a good thing that we can do is allocate a bunch of memory so that when your program is actually running, creating a new element dynamically costs actually less. Do you understand?
Yeah.
Because, for example, in the case of vectors, it's optimizing that by, pre-allocating and, just using memory that is unused, basically. And we are basically doing the same. But instead of a vector, the goal is to potentially have holes in the middle.
Yeah.
Yeah, I guess, it's kind of advanced.
Yeah.
Because with vectors, you basically have unused elements at the end and used elements at the beginning, right?
Yeah.
What we want here is to potentially have holes and to be able to destroy any elements at O1, complexity runtime, and construct 2 at O1.
Oh, I see.
So this is basically optimizing kind of allocations. And yeah, right now we allocate a bunch of things, but we can remove one. And yeah.
And we can reallocate.
And yeah, you can reallocate it whenever you want.
Reinitialize.
Yeah, that's it. So the thing now is that if you want to destroy multiple elements,
it's
kind of tricky, right?
We do a for loop.
A for loop? Like searching every element and see the one that is unused, basically?
Yeah. We can do that.
You could do that. The thing is,
you could do that.
It's ON, and creating a new element would be ON, right? Because you want to find an element that is unused, right?
Yeah.
So what you could do is basically instead have Okay, let's have a list of unallocated, well, basically unconstructed, sorry, elements.
Oui, ouais.
Right?
Ouais.
Ouais. And basically, when you destroy an element, you just insert, I suppose. That's basically right.
Yeah.
Sorry, I'm going to go really advanced, but I hope it's fine. It's to show people what you can do when you understand what's beyond, that. std has no list. Can you save or? Okay.
Can you
insert?
save?
This one is because of that. And is that good?
I don't. Seems to be good.
Oh no. Position and node. That should be const iterator. So the position, we have the position. And or maybe node. Oh yeah, because never mind. Yeah. Okay. Yeah, okay, that's it. So yeah, basically you can have a list with your unused elements, and when you want to create a new element, you can basically just get the last one, right?
Right.
So something like that. And allocate from that. And then just, well, actually just pop back, right? Well, I guess. Right? You can have something like that, right? Azrato?
Yeah. Yeah, I'm here.
Okay.
I'm here.
What's the problem with that?
We don't deallocate the element.
Deallocate. What do you mean?
It's still in the memory.
Yeah, but I mean, we want it to. I mean, yeah, I guess at the end we could destroy that, but.
First, we need to deconstruct the element.
Yeah, I mean, at the end we can have something like a destructor that is destroying all the elements. That's not really the problem. Basically, the thing is that we inserted a list, right? A std list.
Yeah.
And basically it's doing allocations. Because it's a list,
Yeah.
right? So it's not optimizing anything, right?
So we don't need to allocate anymore.
Well, I mean, the goal was to prevent allocations. But we just did allocations. Because every new node of this std list is a new allocation, right?
You're right.
So basically, the thing is that your lists can be inside your allocated memory.
Units can be inside.
So the thing is that when you are not using an element,
Yeah.
you still have memory that is unused, right?
Right.
Okay, so let's actually go into on Whiteboard. Let's go on Whiteboard.
Whiteboard, yeah. I'm on Whiteboard.
Okay.
Whoops.
So follow me.
I'm coming. Where are you? Are you?
Actually,
I see the.
let me do that in blue because it's allocated. Okay, what is in blue is allocated. Okay.
Okay.
What we have is we can potentially create new elements. So we have some. Well, we have some elements still. Well, we are allocating based on elements, right? Because it's a multiple of the size of our struct. So we can have something like that. One element that is created. Another one, etc. Okay?
Okay.
But then we have unused elements, right?
Alright.
And we just said that we could have a list that is basically... This one is pointing there. This one is pointing there. This one is pointing there, right?
Alright.
For the free objects that we can use. But what we can do is actually have one pointer that is saying this one is free, okay?
Yeah.
But then we can have this one is free. This one is free. This one is null. Do you understand?
Not really.
Basically, you can have a list inside what you allocated.
Yeah.
And then, let's say you want to add a new element. Okay?
Yeah.
You can basically check that pointer. Okay? And this is not null. And this is telling you where you can allocate your new element. So basically, this is saying you can allocate your new element here. So now you can construct your new element. And you change the pointer.
Yeah.
And this is basically O1. And you're not allocating anything.
Yeah.
Right?
I understand.
And if you want to instead remove an element, you can just
remove the element
and change the pointer. Yeah, that's it. Actually, no. Yeah, no, never mind. Yeah, that's it. That's it. Just have, basically change the pointers, and that's it. And that's like O1.
Yeah.
O1.
Okay, I understand.
For add and to remove. So I actually have something like that on my GitHub. And I also told you about the Unrolled list, right?
Yeah.
I actually made a new allocator. So, okay. This is actually quiet. Yeah, I have to explain a lot. Allocator. Let me show you. Soup.
Allocator.
Memory soup. I think this is there. And this is it public? Yeah, this is public so people can see. Check my stream or, yeah.
Yeah, I'm currently on your stream.
Okay. Whoop. So, oh, not that.
I haven't had, wait.
So this is memory soup. So you can see the readme if you want.
I haven't had, please wait me.
I just added, sent you the link if you want. Basically, it's for fast allocations and deallocations. It's not really allocations and deallocation, but anyways, you can see that, and basically the default allocator for std vectors and all of that is like std allocator. But what I did was 10 times faster on some benchmarks. And basically, let's see that. So this is templated so that it works for any type.
I think you don't share the good thing on your stream.
Is it? Oh yeah, indeed. Thanks. Oh yeah, because I didn't switch. Okay, so let me show you back. Yeah, optimized, right? This was never done. But anyways, so we have multiple files. And this is basically templated so that it works for any type, just like std vector and all of that. And basically, as I told you, you have what do you have? Well, I guess you have the first node, right? That you allocate.
All
like
right.
you allocate your whole array. Can I show you?
You can show me anything on your stream if you want.
HPP, yeah, I suppose that's just the same. So you can't put templates in .cpp files. So that's why I have a .inl to split the definition and the implementation. But Unrolled list. Yeah, allocate data. So basically I can allocate data with malloc, as I showed you.
Yeah.
And what I do is I allocate the amount of nodes I want to allocate times, well, the size of a node, plus basically, yeah, I guess it's a bit tricky. But basically plus extra data. And what I'm doing is basically I have a pointer towards the next thing to construct. Basically, you know, the three elements. The elements that are not constructed. I have a pointers toward them. And inside, I basically have the node. I have a node pointing to the next element. And that's basically it. And you know, I have my list, and well, basically that's the implementation I told you about. Yeah. Allocate, deallocate. And the thing is, did you know that new is actually it's an operator. New is an operator. Did you know that?
No, I didn't know that.
That means you can overload it. But I don't have it here. But overload overload new C++ reference. Okay, there. Basically, you can overload it. So can I operator new? Wait. Yeah, this is global. Okay. So yeah, gigs for gigs is really good. basically you can you can overload it globally, but you can also overload it for specific types. Same for delete. And basically you can create, overload the new operator like that. And instead of having your new allocate memory every time, you can basically use my allocator that is optimized as we just saw to basically, you can basically optimize new, and the way you use the allocator is the same way as you would use new normally. So that basically means you don't have to worry about new or delete much, like the costs, because you can always optimize that behind the hood.
Okay.
Yeah. I mean, the goal is still to, prevent doing a bunch of useless new and deletes, but you can basically optimize that behind the hoods anyways. So, sometimes just don't micro-optimize, I suppose.
Okay.
Well, wait. Never mind.
Can you overload the add operator, for example?
The plus? Yeah, you can, actually.
Oh, that's really funny.
You can do... You actually had a comma operator.
Yeah.
No, you don't understand. It's been removed because it was really bad.
Why?
Oh, yeah, it's actually there. So you have basically the new operator, new array, delete array. You have co-await since C++20, but you also have plus, minus, times, divided, modulo, the thing, basically all of that. And you also have the spaceship operator since C++20. And you have the comma there.
And why the comma was a problem?
The comma has been removed.
And why?
Because basically you didn't know when it was called. Because you can have commas everywhere, right?
Oh,
so it's a bit complicated. Like, is it calling the comma operator because there is a comma there? That's a good question.
Okay, I see the problem.
So that's why it's been removed. Took some time.
Very funky.
Yeah. But yeah, you can override that. And this is, it can sound kind of weird, like, why would you override operators, right?
If you have custom struct and custom class?
Yeah, but what kind? Basically, you can do that if you have a really big number, for example, with like a custom implementation, right? But you can also do that for vectors.
For example, if you implement complex, for example.
Yeah, a complex number, for example. You can do that for complex numbers. You can do that for vectors. You can do that for matrices, right? You can do that for quaternions, like to use the mathematic meanings of, the thingies. But you can also do that for iterators. Do you know about iterators? No, you don't, because you would have used them over arrays.
It's like a for each loop?
The for each loop is implicitly using iterators. So basically this is equivalent to you using indices. And in
iterator in Java,
Yeah. Remember when you were, basically, when you were looping through an std vector, you were using integers, indices to, basically an index was an element for you, right? It was like a pointer towards an element, right? Right?
Right, yeah.
But with lists, you saw that you couldn't use indices, right?
Yeah.
Right?
Right.
So instead, what did you use?
I use an iterator.
No, you didn't use an iterator directly. Well, what was your iterator, rather?
It was thing.begin.
Well, basically you were using pointers, right? To go, well, to loop through a list. You did use pointers, and you incremented those pointers, right?
Yeah.
Well, you went to the next, basically. And this is it. Basically, an iterator is some kind of abstraction for any container to, for example, go to the next element or access to your element's data.
Yeah.
So this is the first element. This is the element after the last one. But basically, with that, you can just loop with a while loop. And you can count. You can see out. And the thing is, you see this code. This code would work whether you have a vector or a list. Because with both, you can just increment your iterator. Because
I already use iterator in Java. It's
what?
Yeah, I already used iterator in Java.
Yeah.
In Java, there are while as next.
Yeah, that's basically the same thing. But you know what's the difference is in Java and C++?
Not really. There are no as next.
In C++, you have templates, right?
Yeah.
So
override the iterator.
Well, basically, something with templates is in C++ is that templates are known as compile time, but in Java, for example, it's like dynamic. It's like you have polymorphism, right? You have basically, for example, you have the collection. Well, you can have a collection variable that points toward any collection you want, right?
Yeah.
You don't have that in C++.
Okay.
It's not dynamic.
Oh, C++ is bad. Java better.
Well, the thing is, in Java you can have like an abstraction, right? But in C++ it becomes a lot harder, right? Because like if it's not inheriting from the same stuff, that means it's like really tricky. And yeah, iterators are really good if you want some functions to behave the same way on a lot of different containers. For example, if you want to sort a container, sorting an std vector is a lot different from sorting an std list, right?
Yeah.
But if you use iterators, it's like an abstraction to be able to do that. Anyways. But yeah, what I was saying is that for iterators, you can go to the next iterator with ++, for example, or you can go to the previous one with -, or like, you know.
Okay.
So it's like an overload that is actually used by iterators too. And you also have, talking about overloads, you have, as you can see, the times, right? You have that, right?
Yeah. Yeah.
But what you didn't know is that it's not actually just multiplied. It's not actually just the multiplication.
It's also pointers.
Yeah, that's it.
So there's some issue.
Where is that? I don't have it. No. Wait, is it?
No.
Wait, no, actually, no, it's not this one, sorry. Is it? Wait, no, yeah, there is this one too. There is both. Yeah, there is both. You also have the arrow, basically, right? Yeah, it's basically there. Can I show you an example? P operator, std unique ptr. Yeah, that's it. You have also operator boolean if you want to convert to another type implicitly. And you have these ones. And this is why you can use an arrow and dereferencing like a type and not just a pointer. And with the boolean, that's why you can, for example, do that. Just put a inside a if and it's converting to a boolean and it's checking if this is valid or not. Anyways, that's all. Sorry, I think I went a bit overboard.
Yeah, you got a little bit too far for me.
Yeah. But basically you can do a bunch of stuff if you know what you're doing with memory. That's it.
Yeah.
Hey. Till later. But yeah, there's like a bunch of stuff we can still see. We're going to finish for tonight, right? But you have like basically trees, you have hash maps, you have hashes in general. You have, I guess that's the most used. What else? I guess you have algorithms more generally, because we just talked about data structures right now, right?
With programmation, I've learned something very important. The solution to everything is just hash map.
Yeah, this is it.
Everything can be solved with hash map.
Oh yeah, I still want to tell you something.
What do you want to tell me?
This is quite simple, don't worry.
Okay.
It's about some kind of abstraction. Okay, so you can see. Let's go on a whiteboard.
Yeah, I'm on whiteboard with you.
Okay. So I told you about FILO and FIFO maybe, right?
Yeah, FILO first in, last out, yeah.
And FIFO is?
FIFO first in, first out.
Yeah, that's it.
Yeah, it's the pile, it's a stack.
Yeah, that's it.
Where are you? Yeah, you are here. I
Bottom.
see you.
So, anyways. So basically, yeah. Well, first out, I guess you can. Yeah, I don't have to write that. So basically, yeah, this is a stack and this is a queue. A stack is first in, first out is a queue. And this is a stack, right? Yeah, I guess we could. Yeah, I guess we could have done some problems on that. I missed that. I guess it's a bit too late, right? I don't know.
Yeah. Maybe we can do a second episode.
Yeah.
And second stream.
So basically a stack is you have one element, you add another element, another one, and if you want to remove, then you
put the first one.
Yeah, you remove the first one, then this one, and right, and it's basically that. It's first in, last out, because this one is like until the end. It's here until the end, right?
Yeah.
The queue is different. Is you have one element. You have new one, new
second
one,
element,
new one, and if you want to remove, then you remove the last one. because first in, first out.
Yeah.
Right. And yeah, that's basically it, right? And basically you can implement that with vectors.
Yeah.
Because basically, as I told you, for a vector, pop back is 01. Here. Pop back is 01, right? So it's really fast for vectors.
Yeah.
So in the case of a stack, so FILO, first in, last out, what you can do is you have your vector.
Yeah.
You add an element. Now,
Yeah.
now. And if you want to remove, you just remove the last one. So pop back, this is 01, right?
Yeah.
Now for the queue, it's a bit different. Do you see why?
You remove the first one.
Yeah. I guess I could have explained that on the next episode, but that's fine.
But you can do a cliffhanger, whatever you want.
Yeah.
Whenever you want.
So basically, you add an element, add an element, add an element, right? Add.
Yeah, right.
But then you want to remove.
I know.
So this is a bit different from a vector, right?
Yeah. I remove this one and I move the other here.
And then you don't move.
Oh, I don't move?
Because basically you don't need, well, basically you can have something a bit different from a std vector. But what you can have is a container that is basically where you have this space that is allocated but not constructed, this space that is allocated but not constructed, and you can have some constructed space in the middle, and basically you have a pointer there and there. And if you want to add another element, then you just put that there. A new element, you put that there. And if you want to remove, you can just continue, right? And the thing is, you're going to reach the end at one point, right?
Yeah.
But if you want to add a new element, you can just go there. Yeah. Right?
Yeah, I see.
And if you want to remove, whoop, right? And this is basically called a circular buffer.
Because we do zip.
Because it's circular. Yeah, that's it. And yeah, it's optimized because it's O1 insertion and, well, O1, yeah, insertion and O1 deletion, right?
You're right, yeah.
So this is O1. This is O1. And this is continuous, this is continuous. And basically both are amazing, right?
Yeah.
That's it. So this is optimized. This is really good. And you also have something called a Dequeue in C++. Do you know what that is?
No, but you will explain.
Yeah. So I told you how std vectors have basically O1 for pushback and O1 for popback, right?
Yeah.
But it's like really slow with an insert or an erase, right?
Yeah.
But what about pushing front in the front and popping front?
One popping front.
Well, if you remove the first element, it's going to copy all of the following elements, right? To move that.
Yeah. Yeah.
Well, that's how std vector works. But with Dequeue, basically, you have allocated your memory, right?
Yeah.
Then you can construct. But the same way, basically you can just use a circular buffer. But when you remove the first element, you can remove it. And pop front. Pop the first element. You can remove it like that. And if you want to add a new element at the front, then you can just continue, right? Add a new element at the back, you can too.
Yeah, because it's circular.
Yeah. It's just that basically you have, well, it's more, the size is bigger because you have to account for the other memory, basically. Basically, a vector is with a vector, a simple std vector, you have you need rather 1, 2, and 3 pointers. So it's like 3 times 4 times 8, sorry, equals 24 bytes. But with this one, with a Dequeue, with a circular buffer, you basically need 1, 2, 3, and 4. And this is 4 times 8, 20, wait, 32 bytes. Right.
Learn math with progs. Math 101 with progs.
But yeah, it's not really that much of a problem, right? So like Dequeue is like really good, actually. Because Dequeue is for double queue. Double queue? Wait. Well, basically, as you can see, FIFO is like a queue, and it's like a circular buffer, and this one is a circular buffer too. And yeah, Dequeue is for double queue, basically, because you can use the concept of a queue in 2 ways. Like you can push at the front, but also at the back. You can pop at the front, but also at the back. And it's all one. But yeah, most of the time you still use a std vector because you don't really need to, you know, have the first elements optimized for deletion or insertion. Or if you do, then you just use a queue most of the time. Or a stack. You don't need both behaviors. Anyway, that's it.
I prefer stack.
Yeah, the stack is really simple, right? Because
Yeah.
basically it's a vector, right? It's just a std vector, but you use the pop back and like it's really optimized. Like the stack is really great. It's continuous, it's like everything you want. Oh yeah, I remember now. The problem with the stack.
Oh.
There is a problem with the stack. You asked me you asked me before if you could use if you could allocate on the stack like 10 gigabytes, for example, right?
Yeah.
Or like 1 terabyte, let's say, okay?
Yeah, I wonder if 2 terabytes of RAM on my system, you know.
The problem is that the stack is, well, it has a static size. Okay?
Yeah.
For example, well, this is really small, but for example, 256 megabytes, okay?
Yeah.
And the thing is, if you allocate more than that, do you know what's going to happen?
Out of RAM, out of memory. Oof. that it or not? Just out of memory?
That depends. Because
it depends.
it doesn't necessarily detect. Well, I guess now it detects, but before, you know, the old times, it didn't necessarily detect. And like, basically, because if you want to optimize your code, you know, in release, for example, you're going to remove some conditions and some exceptions and all of that. And basically, you could access...
Overflow.
Yeah, that's it. You can... Yeah.
You can crack your Nintendo Wii with that.
You can access data that is not reserved for the program. So you can like for example access files or, well, maybe not. It depends, but data from other programs, for example.
You can crack your Nintendo DS and your Nintendo Wii with an overflow.
Or you could also access the operating system data, for example, potentially. Not really, but basically, yeah, you can abuse that. That's it. But yeah, it's like today we have VRAM instead of just RAM. So, well, I guess never mind. Because it's still the stack. But yeah, no, I suppose it's safe. It's like, for example, you get a seg fault when you do something bad in C++, right?
Yeah.
So you have some securities. But yeah.
I have 5 terabytes of RAM with my FTP, so there is no problem.
But yeah, if you want to hack some stuff, you can do it this way, even if it's a bit old.
I will train my a new AI model with my FTP RAM. That will be very fast, you know.
Yes.
Yes.
Yes. But yeah, basically that's it.
That could be a good video. I try to train my model with FTP RAM. I try to download RAM.
Download RAM
from Google Drive.
But yeah, basically.
Oh.
Basically what? Wait. Yeah. Basically. Yeah, just vectors, and we did see a lot, but like we didn't actually do algorithms. We still haven't done algorithms, right? Oh, I guess we can do stacks and all with trees. Yeah, that's fine. Stacks and queues with trees should be good.
For the next episode?
Yeah. That's what I'm saying, because it can be a single, you know, thing. I'm just searching for standard library. Oh, containers. Containers library. So array. So sequence containers. Array, vector, in-place vector. What's that? Oh my god. C++ 26. What's that?
Oh, we live in the future. We have C++ 26.
That's what I've always wanted. No, because in C++ you have a std unique pointer where you can have a dynamic array, but you don't have the size and you don't have iterators and you can't loop through that. But with in-place vector you can loop through that. Oh, I'm so... Wait, oh no, never mind. No, it's not dynamic, my bad. Wait, what's the difference between that and an array? May vary dynamically up to a fixed capacity. Oh, okay. Up to a fixed capacity. Got it.
Yeah, you put max long for max value.
Wait.
And you're good.
Oh, so it's like optimized. So it's basically the same as std vector, but with a custom allocator. Kind of. Oh, anyways, so we did Hive, what's that? Yeah. Okay, Dequeue we did that, forward list we did that, and list we did that, right? So we actually did most of the, well, all of the current sequence containers. We did all of that. Then we have associative containers and other associative containers. We have container adapters, like stack and queues. We did see that. I guess we do have the priority queue though. And we have some stuff. But that's fine. Well, basically we have all of the sequence containers. That's good. I wanna see that. So yeah, the stack is... wait. Okay, the stack is by default a Dequeue, and the queue is by default a Dequeue too. But a stack, you could do that with a std vector. Back, front, push back. No, this is a queue, so that's fine. So this is a Dequeue, that's why. But with a stack, you have back, push back, and pop back. So you can do that with a list or an std vector. Standard containers, std vector, Dequeue, std lists. Basically, you can implement it in different ways. It's just an abstraction. Anyways. Thank you, Azerto.
Yeah, that was very, very, very hard and very tough.
But you can you can watch the VOD again.
Yeah,
on my YouTube channel.
Speed 4 times.
I'm going to put some chapters, you know, in the description so that you can see the different places where we do different stuff.
And everyone, see you for the episode 2.
Hey, see you.
If there is one, episode 2. See you, everyone.
Bye-bye. Thanks.
Bye-bye.